formed like this. Alright, this combination of curves is what we call by the name electric field line.
Can start and end at the same point.
Yes, so we have seen that an electric field line can start from a positive charge. This curved surface is part of a sphere, right? You compare this with the plane angle. See, there we got an arc. At no point between these two charges will the electric field be zero, because the electric field due to this charge Alright, so here we'll talk about the electric field lines first. So what is an electric field line? So that is simply a visual or a diagrammatic representation of the strength and direction of the electric field due to a charged object. So let us take our first example, the electric field lines due to a positive charge. So this is a positively charged object. It's more like a point charge, a positive charge. So this positive charge has some electric field in the space around it. So at different points in space, it will have electric field in different directions. Let us take one point. So some point in space, somewhere here. Now we have electric field due to this charge at that point in the radially outward direction, away from the charge. As we know, the electric field due to a positive charge will be in the radially outward direction. So this charge has electric field at this point in the radially outward direction. So this electric field is represented by this arrow mark. Alright, so this arrow mark represents the direction of the electric field. Now you take another point along the same line. Okay, on the same line, you take another point. At that point, we have electric field due to this charge in the same direction, right? Same direction. Now at various points along the same line, we'll have electric field, all have the same direction. Alright, now instead of representing this electric field at various points by the small arrow marks, we will join all these points and we'll draw a long line. So what is this line? So this is what we call by the name electric field line. So at various points on this line, we'll have electric field in the same direction as the direction of the line itself. Do you understand? You take any point on this line. At that point we'll have electric field in the same direction as the direction of the line itself. Do you understand? So this is one example of an electric field line. Is that okay? Now similarly, let us take another point. So let us take a point somewhere in space here. So at that point also we have electric field in the radially outward direction. Do you understand? So radially outward direction. So that is another electric field line. Now at different points in space we'll have electric field in different directions. Now so this system of lines is what we call by the name electric field lines. Is that okay? So what is electric field line due to a charged object? So that is radially outward lines. Okay, this system of lines which represent the direction of the electric field at various points. This system of lines is what we call by the name electric field lines. Is that okay?
So an electric field line is the trajectory of a positive charge placed in the field?
Yes, that's correct, but only in this case, not always. Let us take a positive charge and we place it at some point in space. Now this positive charge will move in the direction of the electric field lines only. So the direction of the movement of this positive charge is same as the direction of the electric field lines. So that is correct. But later on, we'll also have cases in which the electric field lines are not straight lines but curved lines. Alright, electric field lines can be curved. In that case, a positive charge placed at some point will not move along the curve always. It will initially tend to move in that direction, but later on as it gains momentum, it will deviate from the path. Alright, but here in this case, all the electric field lines are simply straight lines. So any object placed at some point in space, a charged object, that will move in the direction of the electric field lines only. So only in this case when the electric field lines are straight lines. If they are curved lines, so the path initially will be in the same direction as the direction of the electric field lines, but later on it will deviate from the path because it gains momentum, right? As the speed increases, so that will deviate from the path. Okay, so that comes later on, but for now we only have electric field lines which are straight lines. So in this case, any object will move in the direction of the electric field lines only. Is that okay? So that is our first example of electric field lines. So electric field lines due to a positively charged object. So these electric field lines will be in the radially outward direction. Is that okay? Yes. Okay, now we will take the next case where we will draw the electric field lines due to a negative charge. So this time we have a negative charge instead of positive charge. As we know, the electric field due to a negative charge will be in the radially inward direction towards the charge. So instead of the electric field lines pointing outward, this time the electric field lines are pointing inward. Do you understand? So that is the only difference. So a positive charge has electric field lines in the outward direction, and negative charge has electric field lines in the inward direction, okay, towards the charge, okay, radially inward direction. So that's it. Now combining the two cases that we have discussed so far, right? In the first case, we had a positive charge. The electric field lines start from the positive charge and they terminate at infinity. You understand? The electric field lines start from the positive charge, they terminate only at infinity because there is no endpoint, they reach infinity. Now this time we have a negative charge, so the charges, the field lines start from infinity and they terminate at the negative charge. So where do they start from? So they start from nowhere, right? So we don't know the source. They start from somewhere but they reach the negative charge. So these two cases can be combined together and we can say that what is the starting point of an electric field line? So it can either start from a positive charge or it can start from infinity. So combining these two cases, we come to the conclusion that the electric field lines either start from a positive charge and reach infinity, or they start from infinity and reach a negative charge. So the starting point of an electric field line is either a positive charge or at infinity. So that is the first point you have to remember. Alright, the electric field lines emerge from a positive charge and they reach infinity, or they'll come from infinity and they'll terminate at a negative charge. So these are the only two possibilities. Do you understand? So the electric field lines terminate at a negative charge or at infinity. So combining these two cases, so we can write some points here. The first point that you have to know is the starting point of an electric field line is either a positive charge or infinity. So either the electric field lines start from a positive charge or they'll start from infinity. Do you understand? Similarly, the next point is, what is the terminating point? Where do they end, the electric field lines? So they either end at a negative charge or they'll end at infinity. In the case of positive charge, they start from the positive charge and they end at infinity. In the case of negative charge, they start from infinity, they end at the negative charge. So the ending point, okay, the electric field lines terminate at a negative charge or they terminate at infinity. Alright, so these are 2 points that you have to remember, the starting point and the terminating point of an electric field line. Is that okay? Yes. So these are 2 points we have to remember. So there are many more points about the electric field lines. We will write one by one. Okay. So these are the first 2 points about the electric field lines. Okay. Yes. Okay, in the next case, we will have 2 positive charges. Instead of 1 charge, we have 2 charges now. We will find the combined electric field lines due to these 2 charges. Alright, so these 2 are positive charges. Now let us take some point in space, somewhere here. Now at that point, there will be an electric field due to this positive charge in the radially outward direction. So this is the direction of the electric field due to this charge. Now similarly, we have electric field due to this charge, again in the radially outward direction. So this direction. So the net electric field at that point is the resultant of these 2 electric fields. Alright, so that will be somewhere in the middle. Alright, so this is the direction of the electric field due to these 2 charges. But here, unlike the last case, here we have electric field lines, not straight lines but curves. It will start from the positive charge, it will pass through that point. It is a curve here. So electric field lines can be curves like this, not necessarily straight lines. Do you understand? Now if you consider different points in space, the electric field lines are formed like this. Alright, this combination of curves is what we call by the name electric field lines due to these 2 positive charges. Do you understand? So the electric field lines can be curved lines like this. Okay. Now what is the direction of electric field at any point? See, it is a curve now. In the last case, we had a straight lines. So at any point, if you want the direction of the electric field, that is the direction of the electric field line only, because it is already a straight line. If you want electric field, the direction of the electric field at a particular point, so the direction of the electric field line is same as the direction of the electric field. Okay, no problem with that. But this time it is a curve. The curve has no unique direction, right? At different points, the directions are different. So if you want to find the direction of the electric field at a particular point, what we have to do? Same thing, we draw tangent at that point. Okay, the tangent line is the direction of the electric field at a particular point. At different points on the curve, we have different directions because the tangent has different directions at different points. So at a particular point, you want electric field direction, so you draw tangent at that point to that curve. So that tangent will give you the direction of the electric field at a particular point. Do you understand? So that is our next point, the electric field direction, right? The direction of the electric field at a point is along the direction of the tangent drawn to the curve at that point. You understand? So this is the next point that you have to know. But this problem does not arise in the case of straight line, because straight line itself is a unique direction, right? So the direction is fixed now. So at any point, the direction is the direction of the electric field lines. But in the case of curve, so it has different directions at different points. So at a particular point, you draw tangent That tangent direction is the direction of the electric field at that point. Is that okay? So this is the next point that you're supposed to know. Is that okay? Yeah. Okay, what if you have two negative charges instead of two positive charges? Now there is no difference, same set of electric field lines, but the direction is reversed. Because these are negative charges, the electric field lines start from infinity and they terminate at the negative charge. You understand? In the last case, we had electric field lines starting from the positive charge and reaching infinity, but this time they start from infinity and they will terminate at the negative charge. The direction is reversed, otherwise same set of electric field lines. Alright, so two negative charges or two positive charges, they have electric field lines. These curves, do you understand? This collection of curves, right, is what we call by the name electric field lines due to these two charges. Is that okay? So that is about electric field lines due to two negative charges. Okay. Okay, so here in the next case we have a system of opposite charges. One of them is a positive charge, the other one is a negative charge. Now we have to find the combined electric field lines due to a positive charge and a negative charge. Almost the same idea. Take some point in space. At that point there will be an electric field due to this positive charge in the radially outward direction, and there will be an electric field due to this negative charge in the radially inward direction. So now the resultant of these two electric fields, so that is somewhere between them, right? So this is the resultant, the net electric field due to these two charges at that point. Now join this. So the electric field lines start from this charge and end at that point, right? Because this is the positive charge, and electric field lines start from the positive charge and they'll end at the negative charge. Alright, so this time also we have a curve, right? So this is the curve called an electric field line. Similarly, at different points in space, so we will draw the electric field lines. So these electric field lines start from the positive charge and they end at the negative charge. You understand? Or it can even start at infinity and end at the negative charge, or it will start from the positive charge and they'll end at the infinity. Alright, so this is the combined electric field lines due to a positive charge and a negative charge. Okay, right. Okay, uniform electric field lines. What is uniform electric field? We've already discussed uniform electric field. If you remember, at any point in space, the electric field has the same magnitude and direction. At different points, generally, the electric field will be different. It will have different directions, different magnitudes. But here what happens, at any point in space, the electric field remains the same. Alright?
But how is it possible? The electric field strength decreases as you move away from the charge.
See, generally when you move farther from the charge, the intensity of the electric field decreases. When you get closer and closer to the charge, the electric field strength increases. But we have also done some cases in which the intensity of the electric field does not change with respect to the distance. As you move farther away from the charge, the intensity remains same. So do you remember one such example? See, we have found the electric field due to an infinitely large plane. So what is the formula? That is sigma divided by 2 epsilon 0. Sigma is a constant, so that is the charge density of the plane, so that is constant. So sigma divided by 2 epsilon 0, so that does not depend on the distance, right? So it is independent of x, so the distance. So that means at any point in space, the value remains same because it is infinitely large sheet. The distance x is very small compared to the size of the sheet. So that means, so this remains same. It is independent of the distance. So this is called uniform electric field. So this infinitely large sheet has electric field at any point same, okay, same value, not only the magnitude but also the direction. So that means the electric field lines will be like this, okay, all pointing in the same direction. Do you understand? So the electric field lines due to an infinitely large sheet, so that is uniform. That means they'll have the same intensity and same direction at any point in space. Is that okay? So this is about a uniform electric field. So this is one such example. Uniform electric field. What is uniform electric field? So the electric field remains same at any point in space. Is that okay? Yeah. Okay, now we will consider two electric field lines due to one charge or two different charges, right? Two electric field lines. Can these two electric field lines intersect at a point? Can these two electric field lines have a common point? Is it even possible? Suppose these two electric field lines intersect at one point. So at that point of intersection, let us find the direction of the electric field. Alright, so we have already seen that the direction of the electric field is same as the direction of the tangent line drawn to the curve at that point. But the problem here is, it is not one curve, there are two curves passing through that point. We will draw tangent to both the curves. So if you draw tangent to one of these curves, that will be in this direction. So this is the direction of the electric field. But we also have another curve, we will draw tangent to that curve, that will have electric field in this direction. So we have the two different directions for the electric field at that particular point. But is that possible? At a particular point, the electric field is unique. You understand? It has unique direction. So electric field at a point cannot have two different directions. That means it is a contradiction. So that means we come to the understanding that two electric field lines cannot intersect. If they intersect, that means two different directions for one electric field. So that is not possible. You understand? So that means we come to the conclusion that two electric field lines will never intersect. Okay, so that is one point about electric field lines that you have to remember. Electric field lines will never intersect. Do you understand? So that is one of the points that you have to remember. Okay. Here we have an example of an electric field line which forms a closed loop. Is it possible for an electric field line to have a closed loop? No, right?
Field lines can't start and end at the same point.
Yes, so we have seen that an electric field line can start from a positive charge or at infinity. Suppose this electric field line starts from this charge, that means it is a positive charge. That means this cannot terminate at the same point because this is a positive charge. Electric field lines cannot terminate at the positive charge. Do you understand? So electric field lines cannot start and terminate at the same point. So starting point may be a positive charge or infinity. So suppose this is a positive charge, so it can start from the positive charge but it cannot terminate at the same point. Electric field lines can never form a closed loop. You understand? These are continuous lines. It will never form closed loops. Do you understand? It can start from a positive charge and it will terminate at a negative charge only. Alright, otherwise it will reach only infinity. So closed loops are not possible for electric field lines. Okay, so that is one point about electric field lines that you have to know. Okay. Electric field lines due to a conductor. So we know that in a charged conductor, the charges or the excess charges are always present on the surface of the conductor. The charges are not uniformly distributed over the entire volume. So we can find the charges only on the surface of the conductor. Alright, so the charges are on the surface of the conductor. Now the electric field lines due to these charges are always in the normal direction. That means the perpendicular direction. So the electric field lines always emerge from the conductor only in the normal direction, right? Perpendicular direction. Is that okay?
What if the conductor's surface is concave? Will the field lines intersect?
You mean something like this? A conductor of this shape. So for conductor of any shape, so these electric field lines are always normal to the surface. Okay, something like this. So the electric field lines are always in the normal direction, right? The perpendicular direction. So wherever the electric field lines are drawn, they'll always be in the perpendicular direction. Okay. So even here, but these two electric field lines will intersect. Alright, that's what you are saying. These two electric field lines will intersect each other. No, they will not intersect. These are not straight lines always. You understand? The electric field lines are not necessarily straight line. Initially it is normal. But after that, it will move not in the same direction. It may bend like this. You understand? Electric field lines are not always straight lines, as we know. So electric field lines, initially they start in the perpendicular direction. After some time, so it will move in a different direction because it will no more remain a straight line. It is not necessary that electric field lines are straight lines. So it will bend like this. So electric field lines will never intersect. So initially, when they emerge from the charge, so that will be in the normal direction. Alright. So electric field lines due to a conductor will be in the normal direction, right? In the perpendicular direction. Is that okay? The strength of the electric field at a point is proportional to the density of the electric field lines around that point. See, for example, take a point closer to the charge Q. Okay, so draw a circle. Okay, now the number of electric field lines crossing this area, so that we can call the density of the electric field lines. Alright, similarly you take another point a little farther. Okay, there you draw the circle of the same radius. Now the number of field lines crossing this area, so that is less compared to this point. Do you understand? That means the electric field strength at that point is less compared to the electric field strength at this point, because as we know, closer to the charge the electric field strength is more. Alright, and if you move farther away from the charge, the electric field strength, it weakens. At a point closer to the charge, the electric field lines are closer to each other, which means denser. So that means the electric field strength is more at a point closer to the charge. If you get farther from that charge, the electric field lines are not very close to each other, so it is not very dense. So that means the electric field is weaker there. Do you understand? So the denser the electric field lines are, the more is the electric field strength. Do you understand? So this is one point. So the strength of electric field is proportional to the density of the electric field lines. Okay. See, this electric field strength is proportional to the number of electric field lines. Take for example the charge Q1. There are 4 electric field lines due to this charge Q1. This 4 does not have any physical meaning. See, this is only a representation. There is nothing like 4 lines are sticking out of this charge, right? So this is only a representation, or just to give you an idea of the strength of the electric field, we use the number of lines, right? So 4 lines here. For example, if you take another charge Q2 which has 6 electric field lines, that means we come to understand that the electric field due to the charge Q2 is stronger than the electric field due to the charge Q1, because it has 6 lines, that has only 4 lines. So the number of lines will give you an idea of the strength of the electric field. So it is not necessarily 4 and 6. If it is 40 and 60, so that will give you the same meaning. Do you understand? Only the ratio matters. So 4:6 or 40:60, so they are the same. So the number of field lines, right, that is proportional to the strength of the electric field. So we can say that the ratio of the charges, say Q1 is to Q2, so that ratio is proportional. Okay, that ratio is same as the ratio of the number of electric field lines. So that here is 4:6, or you can say 2:3. So that means the charge Q2 is bigger in magnitude, alright, because this is 3, Q1 is only 2, so 2:3, that is the ratio. Or we can say that this Q2 is 1.5 times stronger. The electric field due to Q2 is say 50% more than the electric field due to the charge Q1, right? That is the meaning of 2:3. 2:3, that means what? 50% more. So Q2 is stronger than Q1 by 50%. So that is the meaning. So the electric field due to a charge, okay, that is proportional to the number of electric field lines. Do you understand? More the number of electric field lines, so more is the strength of the electric field due to that charge. Do you understand? So that's it. Alright, so now we'll summarize all the points about electric field lines that we've discussed so far. First of all, we drew electric field lines due to different types of charges, right? The first one being electric field lines due to a positive charge. A positive charge has electric field lines in the radially outward direction. Alright, all the electric field lines are in the radially outward direction, starting from the positive charge and reaching infinity. Similarly, we have a negative charge. So this time the electric field lines are in the radially inward direction. Okay, now we have two charges, two positive charges. So electric field lines are here, not straight lines but curved lines. They start from these positive charges and they reach infinity. Okay, so now we have electric field lines due to negative charges. So this time the charges start, the field lines start from infinity and they reach, they terminate at the negative charge. Suppose one of them is positive charge, the other one is a negative charge. So these electric field lines start from the positive charge, they terminate at the negative charge, or they terminate at the infinity. Alright, so these are electric field lines due to these charges. We've also done uniform electric field lines, right? For example, electric field lines due to this infinitely large plane. So this plane has electric field constant at any point in space. So all the electric field lines are in the same direction. Alright, so the direction of the electric field lines, so that is fixed. Okay, electric field lines are in the same direction. So this is called a uniform electric field lines. So these are the different types of charges for which we have drawn electric field lines. Alright, and we have also written few points about electric field lines. Alright, see, here are the points. The first point is about the starting point of the electric field lines. These lines will start either from a positive charge or will start from infinity. Alright, similarly the next point, the electric field lines terminate at a negative charge or they'll terminate only at infinity. Okay, and the next point, so the direction of the electric field. So when the electric field lines are not straight lines but curved lines, if you want to find the direction of the electric field, you just draw tangent at a particular point, and the tangent direction is the direction of the electric field at that point. Alright, the tangent will give you the direction of the electric field. Alright, so that is one point, so that you have to know. Okay, And the next point is electric field lines do not intersect. If two electric field lines intersect, at that point of intersection we have two different directions for the electric field. So that is not possible. So electric field lines will never cross each other. Do you understand? They will not intersect. Alright, so next one, the electric field lines will never form closed loops. Okay, because they cannot start and terminate at the same point. Electric field lines will never form closed loops. Is that okay? And then the next point here is the electric field due to a conductor are in the direction normal to the surface of the conductor. Alright, electric field lines emerge from the conductor in a perpendicular direction. Okay, yes, that is the next point. And the next one here is the density of the electric field lines will give you an idea of the intensity of the electric field. So the denser the electric field lines are, so more is the electric field strength. Is that okay? So generally at a point closer to the charge, so the electric field intensity will be more because the lines are closer to each other, which means denser lines. Now similarly, the next point, the number of field lines is proportional to the intensity of the electric field. Okay, so if you draw more number of lines, so that means so the intensity of the electric field due to that charge is more. Alright, so these are the points about electric field lines that you should be familiar with. Alright, yes, so that is about electric field lines. Okay. Alright, so here we'll talk about solid angle. So what is solid angle? See, this solid angle is not as such a part of our physics syllabus, but we learn this so that it will be useful for our calculations involving electric flux later on. So we learn this as a mathematical tool to help us solve some questions related to electric flux. Alright, what is solid angle? See, I'll give you just 5 points about solid angle. Just 5 points that you have to remember about solid angle, right? So the first point here is, so the first point about solid angle is not actually about solid angle but about plane angle or simply angle. We don't generally use the term plane angle, we simply say angle. So what is meant by angle? So we know how to measure the angle between these two lines, right? So this angle generally it is denoted by theta, right? So that is a variable we generally use to denote a plane angle. So this is the angle between these two lines called theta. How do you measure the angle? So we know how to measure the angle, but how is it defined? So usually the unit of angle is taken to be radian. So how is this radian or this angle defined? Okay, see like this, the endpoints of these two line segments are joined by a curve, so we call it arc, right? So this arc subtends the angle theta. So this theta is the angle subtended by the arc. Now you complete the circle which this arc is a part of, right? This completed circle has this arc as a part. Okay, this arc subtends angle theta at the center. Alright, so this angle theta is defined as, so this is the definition of plane angle. So angle theta is defined as the length of the arc divided by the radius of the circle of which this arc is a part. So length of the arc divided by the radius. So that is the definition of radian or generally the angle. So angle or the plane angle is defined simply as the length of the arc divided by the radius. Alright, this is a simple definition. So I hope you are already familiar with this. So this is the definition of plane angle or simply angle. So that is the arc length divided by the radius. Alright, now we are going to define the solid angle exactly using the same terminology, like we'll almost use the same idea to define the solid angle. So as the name suggests, it is a solid angle, which means no more a plane figure, right? So you have to use a three-dimensional view, right? So you have to visualize it. Okay, we can't draw this solid angle. Alright, so let us define now what a solid angle is. Okay. Alright, so to define solid angle also we make use of the plane angle only. See, the angle between these two lines is theta, okay, which is a plane angle because this is a plane figure. So the angle between them is theta, which is a plane angle between these two lines. Okay, now this shape, this is a part of a circle, so we call it a sector, right? This is a sector of the circle. Now the base of the sector or one edge of the sector is along x-axis. That means a horizontal line. Now we will view this in 3 dimension, okay, 3-dimensional view of the same figure. So here we have the base, which is a horizontal line. What we are going to do now, we are going to rotate this sector about that horizontal line. Okay, we get something like this. So what is this shape?
It looks like a cone.
Yes, it looks like a cone. But the base of this cone is not a flat surface, it is a curved surface. Do you observe that? It is a curved surface because we got this surface by rotating that arc, right? That arc is rotated, so we get a curved surface. So this curved surface is part of a sphere, right? You compare this with the plane angle. See, there we got an arc, right, which is a part of a circle, but here we have a curved surface which is part of a sphere. Do you understand? So there we had a two-dimensional figure which is a circle, but here we have a three-dimensional figure which is a sphere. So that is the only difference. So this angle subtended by the curved surface is what we call by the name solid angle. Do you understand? It is not a plane figure, it is a solid angle. So more like a cone, okay, angle of the cone. So this is called a solid angle. Do you understand? So solid angle is defined like this. So the solid angle usually denoted by the symbol omega. So this is omega, right, capital omega, not this small omega. Capital omega denoted by this symbol is defined as the area divided by the square of the radius, just like how we define the plane angle, which is the length divided by the radius. Here we have area divided by the square of the radius. So what is the area? Which area we are talking about? See, the area of the curved portion, which is a part of the sphere. Do you understand? So the curved part has area something, so that area divided by the square of the radius will give you the solid angle. Do you understand? So this is how a solid angle is defined. You should be able to compare this with the plane angle, right? So there only arc, but here we have a curved surface. So this curved surface has some area, so that divided by the square of the radius of the sphere which this curved surface is a part of, right? This curved surface is a part of a sphere having radius r, so r squared. So area divided by r squared will give you the value of the solid angle. Do you understand? So this is how a solid angle is defined. So this is our second point, which is about the solid angle, the definition of solid angle. Do you understand? Okay, so the next point about the solid angle is but before that, we'll also talk about the unit of solid angle. See, the unit of solid angle is denoted by SR, so that is called a steradian. Just like radian is the unit of plane angle, so steradian is the unit of solid angle, right? It is one of the supplementary units, right? Along with the 7 fundamental units, we have radian and steradian as the supplementary units. Do you understand? So steradian is the unit of solid angle. Alright, yes. So solid angle is defined as this area divided by r squared, which has unit steradian. Okay. So here we will write a relation between the plane angle and the solid angle, because we got the solid angle only by rotating the plane angle, so there must be some relation between them. The angle theta, right, subtended by the arc, so that arc or this sector is rotated to get the plane angle. So that plane angle and the solid angle have this relation. So this is the relation between the plane angle and the solid angle. The solid angle, so that is omega, so that is given by 2 pi multiplied by 1 minus cos theta. So this is one relation that you are supposed to remember, right? So the solid angle is 2 pi times 1 minus cos of the plane angle. Okay.
Can you prove this?
See, the proof of this is not at all relevant to our discussion. I want to skip it. Okay, if you insist. Okay, let us prove this. Alright, so what is the formula for the solid angle? So that is given by the area divided by the square of the radius. Alright, so radius is known, so we need to find the area of the curved part of the sphere. You understand? So that sphere, okay, the curved part, so that has area what? That's what we need to find. So simply divide that by the radius, we will get our required answer. You understand? So let us find the area. For the complete sphere, we have the area, right? The curved surface area of a sphere. So that is 4 pi r squared, right? So that we know, but it is not a complete sphere, only a part of a sphere. So we have to find that part area. Alright, so how will you find that area? So we have to make use of integration. Alright.
Integration. I don't want the proof. Drop it.
No, I've started, I will complete it. You asked for it, so you deserve it. See, let us find the area using integration. So let us find the area of that small portion, so which is in the shape of a ring, right, like a circle having some thickness. Let us find the area of only that small portion, and using integration we'll be able to get the area of the entire region. Okay, let us find the area of that small part. So that you can use the formula length multiplied by breadth, right? It's not a rectangle, but still, because that thickness is very small, right, the breadth is very small, we can consider this to be a long rectangle. You understand? Instead of a curved portion. See, or if you cut this ring across and you stretch it, okay, you straighten it, it will be a rectangle. So it is more like a rectangle because that thickness or the breadth is very small. So what is the area of rectangle? That is length multiplied by breadth. But what is the length? That is the circumference of the circle. So what is the circumference of the circle? 2 pi r. So that is the length. What is the breadth? So that is that thickness, right? So that you have to find. So we have to use this idea. see, for a circle or an arc, okay, so the radius is known, the angle subtended by the arc is theta. What is the length of the arc? What is the length of the arc? So that has the formula r multiplied by theta. So this is the formula for length of arc. Okay, so this formula you have to remember. Alright. So length of arc is r multiplied by theta, and the length of the arc only is the breadth. Okay, length of the arc is the breadth. So what is that here? R multiplied by, so here it is, r multiplied by the angle subtended by that arc. So that is taken as, say, d alpha, right? So d alpha. So that's all, r multiplied by d alpha, that is the breadth, and length is 2 pi r, which is the circumference of the circle. So that means our area here is 2 pi r length multiplied by the breadth, which is r times d alpha, divided by r squared. Alright, yes. Now this capital R is a constant, which is the radius of the entire sphere. So that is a constant. But this small r is not a constant. That is only the radius of that ring, right? Circular portion. So that r is not a constant. It's a variable. So r is a variable and alpha is also a variable. Two different variables we have. Now we have to convert one in terms of the other. So can we write this r in terms of alpha? So let us simplify this. So 1 r gets cancelled. So it is 2 pi divided by r. So if you consider that right angle triangle, that opposite side is r, similarly the hypotenuse, that is the radius, which is capital R, so we can use the projection, right? R simply use trigonometric ratios, right? So sine alpha equals r divided by capital R. So that means the small r is capital R times sine alpha. So this is simply r sine alpha d alpha. Do you understand? So now we've got everything in terms of alpha only. The only variable here is alpha. So that means, so let's simplify this. So this is only the area of not the entire region that we are trying to find. It is only the area of that small portion. So we have to denote this by d omega. Understand? So d omega is this one, because it is only the area of that small ring. So now we have to find that omega. So that is the area of the entire region. So integration. Okay, so let us do the integration. So this r gets cancelled, so 2 pi, and then the integration of this, integration of sine alpha d alpha. Do you understand? So this integration will give you our required answer. But what is the limit of this integration, right? Alpha ranges from, see, alpha starts from 0 to theta. You understand? 0 to theta. Theta is the maximum angle. So 0 to theta. So that's all. Just do the integration. You will get the answer. So what is this value? So this equals 2 pi multiplied by, so sine alpha integration is minus cos alpha. If you substitute the upper and lower limits, so 0. Cos 0 is 1 minus and cos theta. Alright, the upper limit. So cos theta. 1 minus cos theta. So that's all. So this is the relation. So the solid angle equals 2 pi times 1 minus cos of the plane angle, right? So this is the relation between the solid angle and plane angle. So that you have to remember. Is that okay? So if you know the plane angle, okay, theta, so we can find the solid angle and vice versa, right? So that's all. So this is one formula that you should be familiar with. Okay. So what is the total angle subtended by the entire sphere? So we found the solid angle, which is the angle subtended by a curved portion of the sphere. But what if you consider the entire sphere? So what is the total angle subtended? See, compare this with the two dimension, right? What is the total angle subtended by the entire circle? So that is 360 degree, right? 2 pi. 2 pi is the total angle by the entire circle. Similarly, what is the angle subtended by the entire sphere? You understand? So let us find the angle subtended by the entire sphere. So we can do it by two methods. So if you use this method, see, what is the formula for the solid angle? So that is area divided by the radius squared. But what is the area of the entire sphere, the curved surface of the sphere? That is 4 pi r squared. Alright, so divided by r squared. So that's also, that is the answer, 4 pi. So 4 pi is the total angle subtended by the entire sphere. So just like 2 pi, which is the angle subtended by the circle in two dimensions. Similarly here, the sphere subtends angle 4 pi. Or we can also do by this method. So we have the formula. So that is omega. So that equals So 2 pi multiplied by 1 minus cos theta. So we have the relation between the angle theta, which is the plane angle, and the solid angle. Now using this also we can get the same answer. See, what is the angle theta to cover the entire sphere? So the angle theta must be equal to 180 degrees, right? So 180 degree pi. Alright, so if theta is pi, it will cover the entire sphere, right?
But the whole circle subtends angle 360 degrees.
No, it is not 360 degrees, it is just 180 degrees. See, you observe that you only take angle in the first half, right? The upper half. See, take angle theta, only the upper portion. But that covers the entire region, right? So, upper and lower part also is covered. See, for example, you take angle from 0 to 90, okay? 0 to 90. But that curve or that sector covers the entire hemisphere, right? Upper and lower, the whole hemisphere is covered if you take angle theta 90 degrees. Okay, what if you take theta 180 degrees, 0 to 180 degree, and if you rotate it, it will cover the whole sphere. Do you understand? So it is not required to take angle theta 360 degree, because only the upper part you take, the upper arc, okay, that covers the entire sphere. So it is just enough to take the angle theta to be 180 degree, it will cover the whole sphere. Do you understand? Take theta equal to pi, so cos pi, so that is minus 1. So 1 minus minus 1, so that will give you the answer. So 4 pi. Do you understand? So this equals 2 pi multiplied by 2. So 4 pi. So that's it. So 4 pi is the total angle subtended by the entire sphere. Do you understand? So this is one point that you are supposed to remember. So 4 pi is the total angle subtended by the entire sphere, just like 2 pi, which is the total angle subtended by the circle at the center. Okay, similarly here in 3 dimension we have angle 4 pi steradian. Okay, yes. Let's consider this example. So there is a charge Q1 due to which we have some electric field lines. There is another charge Q2 which also has some electric field lines. Now you tell me which of these charges, Q1 or Q2, is bigger in magnitude. Obviously Q2, because Q2 has more number of electric field lines compared to the charge Q1. So obviously the electric field due to this Q1 or Q2 is stronger, right, compared to Q1. Is that okay? So more number of electric field lines, so more is the strength. Okay. Now let us consider this angle between two adjacent electric field lines. In the first case, alright, two adjacent electric field lines, let's find the angle. Not the plane angle, but the solid angle. Okay, so that angle is denoted by, say, omega 1. Alright, that is the solid angle between two adjacent field lines in the first case. Similarly, in the second case, so we'll find the angle, and that is denoted by omega 2. You tell me which of these angles is bigger, omega 1 or omega 2? Obviously omega 1 is bigger, right? So omega 1 is bigger because the number of lines is less, so the angle is more. So omega 1 is bigger than omega 2. So now we'll find a relation between this angle omega and the electric field strength due to these charges. Alright, so what is the relation? So the first one has less electric field strength compared to the second one, but the angle is more. In the first case, the angle is omega 1, which is more than omega 2, but the electric field strength has this inverse relation. Do you understand? So the more the strength, less is the angle. Do you understand? So more the strength here, less is the angle. So there it is reverse, right? So the electric field strength due to Q1 is less, but the angle is more. So that means this is the relation, the electric field strength, okay, say E. So that is inversely proportional to the solid angle, okay, omega, right? Inversely proportional to the solid angle omega. But the electric field strength is inversely proportional to solid angle. That means the ratio is the reciprocal of the ratio of the angle, okay, the ratio of the electric field, or ratio of the magnitude of the charges, say Q1 divided by Q2. So that equals the reciprocal of the ratio of the solid angle between these two adjacent electric field lines. Okay, so that equals, say, omega 2 here divided by omega 1. Alright, so Q1 divided by Q2, so here reciprocal, omega 2 divided by omega. Okay, so inverse relation. So when the angle is more, right, so bigger angle, so less is the strength. Okay, smaller angle, so more is the strength. Do you understand? So Q1 divided by Q2 equals omega 2 divided by omega. So this is also one relation that you should be familiar with, so which is required for solving some questions. Is it okay? So that's it. So these are the points related to solid angle that you should be familiar with. So here is the list of all concepts in solid angle that we have discussed. So keep this for reference while we solve questions related to solid angle. There are not many numerical questions based on this solid angle and electric field lines. Let us take few examples. Okay. Three positive charges of equal value Q are placed at the vertices of an equilateral triangle. The resulting lines of forces should be sketched as in. Okay, so here three positive charges are given, so due to which we have some electric field lines. Now which of these options best represent the electric field lines due to these three positive charges? Alright, so let us take it one by one. So the first one, so can this represent the electric field lines due to these three charges? No, why?
Electric field lines cannot end at a positive charge.
Alright, so as we know, electric field lines start from the positive charge and terminate at a negative charge or at infinity. But here, all the three charges are given to be positive. So electric field lines start from a positive charge and also terminate at a positive charge. So not possible. So the first one is not the proper representation of the electric field lines due to these three positive charges. Alright, done. So what about the second one? So is it possible the second one can represent the electric field lines due to these three charges? No, right? So closed loops, right? So electric field lines cannot form closed loops. So second one is also not possible. So what about the third one? Let's take the fourth one. So fourth one, not possible. Again, closed loops. So no closed loops. So fourth one is not the proper way to represent the electric field lines. Okay, next one. So it's just we are left with the third option. So that must be the answer, right? So here the electric field lines start from the positive charge and terminate at infinity. Alright, so all these electric field lines start from all the three positive charges and they terminate at infinity. So that is the correct way to draw the electric field lines due to these three positive charges. So that's also, that is the answer to the question. So very simple, right? A few electric field lines for a system of two charges Q1 and Q2 fixed at two different points on the x-axis are shown in the figure. These lines suggest that here two charges are given Q1 and Q2 due to which we have some electric field. A few of the electric field lines are given using which we need to check which of these charges is bigger in magnitude. We also need to find the point at which the electric field is zero. Alright, so let us do it one by one. First let us compare these two charges. Alright, now you tell me which of these charges is bigger in magnitude. So before that we need to know whether the charges are of same nature or opposite nature. Is the charge Q1 positive or negative? The charges or the electric field lines emerge from the charge Q1. So that means it must be a positive charge. As we know, electric field lines emerge from the positive charge, which means the charge Q1 is positive. And these electric field lines terminate at the charge Q2. So Q2 must be negative. So Q1 is positive and Q2 is negative. Now, which one is bigger in magnitude? So now we have to count the number of electric field lines. So as we know, the number of electric field lines is proportional to the strength of the electric field. Alright, so now how many electric field lines emerge from the charge Q1? So that is, we just have to count. Alright, so there are 13 lines. So 13 lines emerge from the charge Q1. Similarly, how many electric field lines terminate at the charge Q2? So that we have to count. So 9, right? 9 electric field lines terminate at the charge Q2. So that means the ratio, alright, that ratio, only the magnitude, okay, ratio here. So Q1 by Q2, okay, only the magnitude. So we just need the magnitude. That ratio of the charges Q1 is to Q2. So that ratio is same as the number of field lines. So that means this equals to 13 divided by 9. So this is the ratio of the magnitudes of the two charges. Okay, now that means obviously Q1 has magnitude bigger than the magnitude of Q2. Alright, so Q1 is bigger in magnitude because this is 13, so this is only 9, so that ratio is known. So that's all. So this is answer to one of the questions. So okay, now we have to find the point at which the electric field is 0. Okay, so now we know that, so Q1 is a positive charge which is a bigger magnitude. Alright, Q1 is a positive charge and Q2 is a negative charge but is smaller in magnitude. Now at which point is the electric field 0? Is it a point between these two charges, somewhere between these two? No, because these two are of opposite nature. One is positive charge, one is negative charge. At no point between these two charges will the electric field be 0, because the electric field due to this charge, positive charge, will be away from the charge in this direction, forward direction. Now electric field due to the negative charge, that will also be in this direction because towards the charge. So these two electric fields, they don't cancel each other. So electric field at any point between these two charges will never be zero. So the only possibility is here. Or if you remember this idea, the electric field is zero at a point closer to the smaller charge. Okay, outside the line segment, because these two are of opposite nature. So outside the line segment, closer to the smaller charge. So here, okay, so here is the electric field 0. So the electric field is 0 at a point to the right of the smaller charge Q2. You understand? So this is the idea we have discussed in electric field. So the electric field is 0 at a point closer to the smaller charge, the charge of smaller magnitude. So that is Q2 here. So, but here the charges are of opposite nature. That means it cannot be between these two charges, but outside the line segment joining them. Do you understand? So that's all. So this is the answer. So the electric field is 0 at a point to the right of the charge Q2. Alright, so that's all. So that is the answer. The angle between two symmetric field lines due to the charges Q1 and Q2 are given in the figure. The ratio of the magnitudes of the charges Q1 and Q2 is. So here the charges Q1 and Q2 are given. Two symmetric electric field lines emerge from the charge Q1 and they terminate at the charge Q2. So that means we understand that the charge Q1 is positive because electric field lines start from that, and similarly Q2 is a negative charge as the electric field lines terminate at that charge. Alright, now, but we need only the magnitude. Okay, we have to compare the magnitude. So the ratio of the magnitude of the charges, so that is given by, so we have written a formula. If you remember, the electric field strength or the charge is inversely proportional to the solid angle. Alright, so this is one relation we have written. So inversely proportional, that means the ratio of the charges. So that is Q1 divided by Q2. So this ratio is the inverse ratio of the solid angle. So that means this is omega 2 divided by omega 1, which is only the magnitude. Okay, because one of the charges is negative, we just need the magnitude. So this is the relation. Okay, but this is not given in the question. The solid angle is not given, only the plane angle is given. So let us write the relation between the solid angle and the plane angle. So what is the relation? So that is 2 pi multiplied by 1 minus cos of the plane angle. You understand? The solid angle is 2 pi multiplied by 1 minus cos of the plane angle. So what is the plane angle here? No, not theta 2. It is half of that value. It is not theta 2. It is theta 2 divided by 2. See, only half of the angle if you rotate, you get the whole solid angle, right? So, but here the full angle is given. So the whole angle is theta 2. So that is not required. So we only need half of the angle. If you rotate that, we'll get the whole solid angle, right? See, that is how we did the derivation if you remember. So this is theta 2 by 2. So that is the the plane angle, okay? Not theta 2. Theta 2 divided by 2. Now similarly, what is this angle? So here it is similarly, so 2 pi multiplied by 1 minus cos of theta 1 divided by 2. So that's all. So that is the relation, the ratio of the charges Q1 by Q2. So that is given by this. Alright, but we have to simplify this. 2 pi gets cancelled. 1 minus cos theta 2 by 2. So what is the formula? So we have to use some trigonometric identities. So do you remember this formula? So 1 minus cos A. 1 minus cos A equals 2 sine squared A by 2. So this is one trigonometric relation. Alright, so let us use that relation to simplify this. This 2 pi gets cancelled here, and then this will be 1 minus cos A. So that is 2 sine squared A by 2. So this half of this value, that is theta 2 divided by 4. And similarly this one, so that is 2 sine squared theta 1 divided by 4. So that's also, that is the answer. If you cancel this, so this will be sine theta 2 by 4 divided by sine theta 1 by 4, the square of that. So that's all. So this is the ratio of the magnitudes of the given charges Q1 by Q2. Do you understand? So that's also, that is the answer to the question. So this relation is important, the relation between the plane angle and the solid angle. Okay, so this is the relation. And also the electric field strength is inversely proportional to the solid angle. You understand? So that is the relation we have used here to get this answer. Alright, yeah. A spherical shell of radius r is cut into two parts by a plane at a distance a from the center. The surface area of the smaller part of the sphere is. Here a sphere is cut into two parts by a plane at a distance a from the center. We need to find the curved surface area of the smaller part of the sphere. Now we know that the area of the entire sphere, right? So the curved surface area of the entire sphere, so that is 4 pi r squared. But we don't want the entire area, we only want the curved portion of the smaller part. Alright, so we will find that area only. Alright, now we know the relation between the solid angle and plane angle, right? So we have to use the concept of solid angle. So we know the relation, the solid angle. Okay, so that equals 2 pi multiplied by 1 minus cos of the plane angle, which is theta. Okay, but what is the formula for solid angle? So that is area of the curved part. So that is area divided by the square of the radius r squared. So area by r squared, that is the definition of solid angle. So this equals area divided by r squared. So that is the same value. So 2 pi multiplied by 1 minus cos theta. Okay, now what we need is area. So area here is just multiply. So area is 2 pi r squared multiplied by 1 minus cos theta. That's it. All these values are known. So we have to find cos theta. Okay, so there is a right angle triangle here. So just find cos theta from that. So that will give you the answer. So that is 2 pi r squared 1 minus. So in that right angle triangle, what is the value of cos theta? So here you see, so the distance is a from the center, which means the base. So that is a, and the hypotenuse is the radius of the sphere. So that means it is simply a divided by r. That's also, this is the answer. If you want, you can multiply this r squared inside. So that will be, it is 2 pi multiplied by r squared minus ar. Okay, so that's it. So that is the required answer. Alright, so we'll write it in the form which is given in the question. So that is 2 pi r multiplied by r minus a. So that's all. So this is the required area of the curved portion of the smaller part of the sphere. Do you understand? So to find the area, we use the solid angle. Usually to find the solid angle, we make use of area. So here we need area. So to find the area, we use the solid angle concept. Do you understand? See, this is not a physics question. Just to get used to the idea of solid angle, so we have done this question. Alright, so the area of the curved portion can be found using this solid angle idea. Alright, yeah. So here ends our discussion on electric field lines and solid angle. In the next class, we will be doing electric flux. Bye for now.